Continuing our study of arithmetic functions, we're going to look more at multiplicative functions and the concept of perfect numbers in this section. So first we'll prove a correspondence theorem for the divisors of a product of two relatively prime numbers, a and b. We'll look at sums of the type sigma f of d and sigma f of d g of n over d over the different divisors of n. In particular, we'll look at the sum of the Euler phi function, sigma d divides n of phi of d. We'll talk about the three-step procedure for evaluating multiplicative sums of the type right here. And then we'll define perfect numbers, abundant numbers, and deficient numbers, and finally prove the Euclid-Euler Theorem for characterizing the even perfect numbers. Correspondence theorem. That a and b be positors that are relatively prime. I'll let capital D sub a and D sub b denote the sets of divisors of a and b, and the same notation for the divisors of a, b. Then I claim there's a one-to-one correspondence between the ordered pairs of the divisors of a with the divisors of b and the divisors of the product. And the correspondence is given by the function eta, where eta of an ordered pair, d1 comma d2, is equal to the product, d1 times d2. The inverse of eta, and being a one-to-one mapping, it has a inverse function, is given by beta, which is mapping from the divisors of the product to the ordered pairs, and it's given by beta of d is the GCD of a and d, comma, the GCD of b and d. So, what does it take to show something's a one-to-one correspondence? We have to show that the mapping is one-to-one and onto. So let's first show step one, that eta maps into DAB. So that's step one. And that's trivial. All this is saying is that if D1 is a divisor of A and D2 is a divisor of B, then D1 times D2 is a divisor of A times B. And I'll let you fill in the details on that if you like. Two, now let's show that it's a one-to-one mapping. So we have to suppose that eta of d1, d2 equals eta of d3, d4, say. Well, that would imply that d1 times d2 equals d3 times d4. Okay, now what type of objects are these? So d1 and d3 are divisors of A. Let's put it like this. D1 divides A, D3 divides A, D2 divides B, and D4 divides B. So by definition, these are ordered pairs in dA cross capital DB. So since A and B are relatively prime, and in this theorem it's a good idea to put GCD because we have both ordered pairs and GCDs going along for the ride here. So since the GCD of A and B is 1, it follows that the GCD of D1, which is a divisor of A, is relatively prime to D2 and D4. So let's say that D1 is a value relatively prime to D4. Then this equation says that D1 is a divisor of D3, D4. So we have D1 divides d3, d4, and it's relatively prime to d4, so by Euclid's lemma, d1 divides d3. You might recognize this is the same proof you do to show uniqueness of every rational number has a unique reduced form. You run into exactly the same type of equation here. d1 divides d3, and then by symmetry, d3 divides d1, and since they are both positive numbers, d3 equals d1, and then consequently coming back to the start equation here, d2 equals d4. And that proves uniqueness. So we have a one-to-one mapping, and now we want to show it's onto so let's let D be a divisor of the product. And we need to find a D1, D2 an ordered pair in dA cross dB with eta of d1 comma d2 equaling d to show that it's an onto mapping. Well, that's equivalent to showing that d1 times d2 equals d. So the question is, how do we define d1 and d2? Well, since d divides ab, if I look at the GCD of d with a times b, this is equal to d, right? Because d is a common divisor of both of those numbers. Now in your homework, you proved a formula that said this GCD is the GCD of d with a times the GCD of d with b. Why is that? Because a and b are relatively prime. Aha! Let's call this object d1, right? That's some divisor of a. And let's call this object d2. It's a divisor of b. So then d1 divides a, d2 divides b, and we have the desired goal that what? D, which is the GCD of D and AB, equals D1 times D2. QED. So not only have we shown that it's onto, but this part right here is telling us what the inverse mapping does. So if I want to get the inverse, starting with an element D on the right-hand side, the object we want to send it to would be D1 comma D2, just as we've defined it right here. Okay, this correspondence theorem will be very useful for constructing new types of multiplicative functions. So let's recall our definition from last time. A function is multiplicative if whenever a and b are relatively prime, f of the product is the product of the f's. And then we pointed out this evaluation formula right here. So I want to turn to sums of the following type. Suppose we start with a given multiplicative function, little f. And I define a capital F function to be this. Capital F of n is equal to the sum over the positive divisors of n of little f of d. Then the claim is capital F is also a multiplicative function. So given one multiplicative function, we can create a new multiplicative function by summing over the divisors of n. Proof. So let A and B be natural numbers that are relatively prime. And we must show that capital F of AB is capital F of A times capital F of B. So what is capital F of AB? Then, capital F of AB means sum over the divisors of the product of little f of D. Now, by the correspondence theorem, the divisors of the product can be broken down into a double sum where we say D1 is a divisor of A and D2 is a divisor of B, and we have that D1, D2 is the value D we have right here. Okay, so this is by correspondence theorem. So that's the sum over the divisors D1 of A times the sum over the divisors D2 of B of F of D1 times D2. Now what do we know about little f? Little f is given to be multiplicative. And what's the relationship between D1 and D2? So since AB equals 1, it follows trivially that D1 and D2 are also relatively prime. Because if D1 and D2 shared a common prime factor, so would A and B. Therefore, this will equal f of D1 times f of D2, since f is multiplicative. Little f is multiplicative. Now what are we looking at here? This is really just, we've separated the variables, so we can say this is the sum over the divisors of A, like that, times the sum over the divisors of B, of f of D2, by the distributive law. And the first sum is exactly capital F evaluated at A, and the second sum is capital F evaluated at B. QED. F of AB is the product of the capital F's. Examples. The divisor function tau, remember, can be expressed in this manner. Sum over the distinct positive divisors of n of the number 1. So just 1 plus 1 plus 1 plus 1, however many times we have divisors. So think of this as being a function right here. So I'll define capital F of n to be 1 for all natural numbers. Then capital F is trivially multiplicative. Right? F of A times B is 1, which is f of A times f of B, 1 times 1. In fact, it's totally multiplicative. And so by the previous theorem, this is a multiplicative function. It's now, we can write it like this. It's the sum over D dividing n of f of D, where f is this identically one function. Thus, by the theorem, tau of n is a multiplicative function. Likewise, the sigma function. In fact, let's go right to sigma k, the sum of the kth powers of the divisors of n. So this time I'll define capital F of n to be n to the k power for all natural numbers n. That's also multiplicative. F of AB is AB to the k, which is a to the k, b to the k, which is f of a, f of b. It's totally multiplicative. And so, once again, by the theorem, sigma k is a multiplicative function. So in particular, the sigma function itself, that's when k is 1, is a multiplicative function. All right, here's a new example. Let's take the sum over the divisors of n of the Euler phi function. And I claim we get a nifty formula that sigma d divides n of phi of d is always equal to n for all positive integers n. So proof. First we note that since phi is a multiplicative function, so is the sum function. Let's give it a name. Capital F of n, which is defined to be sigma d divides n of phi of d. And that's by our theorem. Okay, and we proved phi was a multiplicative function back when we did the Chinese remainder theorem. Okay, so that's step 1. Then I want to evaluate the capital F function at a prime power. So for any prime power p to the e, what do we get for capital F of p to the e? So that's the sum over the divisors of p to the e of the Euler phi function of d. And the divisors would be 1, p squared, up to p to the e power. And we just add that up. So phi of 1 is 1. P minus 1, p squared minus p cubed minus p squared. What type of sum do you see coming out here? Well, you should recognize this sum as a telescoping sum. So the p's here cancel, p squared cancels, p cubed cancels, and the only thing that survives is this term, and the 1's also canceled out. So that all boiled down to p to the e. So f of p to the e is p to the e. It's the identity function. And then part 3, let n be arbitrary, n be p1 to the e1 times pk to the ek, just be any natural number. Then capital F of n, by the multiplicative property, is f of p1 to the e1 times f of pk to the ek, which is just the same thing we started with, p1 to the e1, pk to the ek, which is n. So think of there being a 3-step process to this proof, and that completes it. Now I want to give you another way to think about this theorem, or think about the proof, in terms of a cyclic group. So let's let Cn equal G be a cyclic group of order n. Let D be any divisor of n. And I just want to count how many elements of order D are there in this group. Well, we saw this earlier. We saw earlier that there exist phi of D elements in the cyclic group of order D. And every element in that cyclic group has some order which is a divisor of n. And therefore, if we take the number n, we just partition it, we partition the group into the subsets of elements of different orders. So we would have phi of 1, that's the number of elements of order 1, and then phi of D1, phi of D2, we just sum over the different divisors. There's a generalization of the theorem we just went through, and the proof is almost identical. So if we start with two different multiplicative functions, little f and little g, and I form this convoluted function over the divisors of n, of f of d times g of n over d, then again we end up with a multiplicative function. And so the proof, you just say let a and b be relatively prime numbers, then f of ab is the sum over the divisors, and notice we're just going to be repeating what we did before, which means sum over the divisors of a and the divisors of b, f of d, g of n over d, where d1 times d2 is how we're breaking up the divisor d. So sum over the divisors of a times the sum over the divisors of b, f of d1, d2, and then n is ab in this case, so n is the product a times b. So I'm going to go a times b over d1 times d2, and think of it like that. d1 is a divisor of a, and d2 is a divisor of b. And now little f and little g are both multiplicative, so I can break that up. F of d1, f of d2, g of a over d1, g of b over d2, and this breaks into a product just like we saw before. And let me just save a step here and say as before. So it generalizes what we did, because you could take the little g function to be a function that's identically 1. So a special case is just let g of n be identically 1, and that gives us the theorem we'd already proven. So again, the three-step process for evaluating any multiplicative sum of this type is exactly what we did for the Euler-Phi function theorem. You first observe that little f and little g are multiplicative functions. So that has to be the condition you start with. And therefore, by the theorem, we get to conclude that capital F is multiplicative. Then you evaluate capital F at any prime power. Very easy to sum over the divisors of a prime power. You just let d be 1 and let d be p. And notice that you're always summing over the complementary divisor pairs like this, all the way down to f of p to the e g of 1, and you just calculate that sum. And then finally use the fact that f is multiplicative to get the value at an arbitrary integer. All right, let's apply the fact that sigma is a multiplicative function to the concept of a perfect number. This is a concept that goes back to Euclid, 300 BC. So a positive integer is called perfect if it equals the sum of its proper divisors. So in other words, sigma of n equals 2 times n. The factor of 2 comes because we have to add n to the number as well to get sigma of n. N is called deficient if it doesn't have very many divisors, so the sum of the divisors comes out to be less than 2n, and it's called abundant if sigma of n is greater than 2n. So the first few perfect numbers are 6. 6 is 1 plus 2 plus 3. And 28, that's 1 plus 2 plus 4 plus 7 plus 14, right? 3, 7, 14, 28. I'm just summing the proper divisors. 496, let's not even try to write down. But what I do want to do is look at the factorization of these numbers. So how does 6 factor? It's 2 times 3. And then 28 is 2 squared times 7. 496. Well, let's go one step further here. Notice that 7 is 2 cubed minus 1. And that 3 is 2 squared minus 1. So these are things that Euclid had observed long back. You have this type of pattern right here. And then here we would have 2 to the 4th, 16, times 31. 16 times 31 is 496. And that's 2 to the 4th. And lo and behold, 31 is again 1 less than a power of 2. And it's the next power of 2 after 4. 2 to the 5th minus 1. And 8,128 is 64, 2 to the 6th, times 127, which is 2 to the 6th, times 2 to the 7th minus 1. Well, you can see a striking pattern going on here. And there is some missing numbers in this list. So what is missing? We've got right between here. I don't have 2 to the cubed times 2 to the 4th minus 1. And what's the difference? And also between these two, there's a missing 2 to the 5th times 2 to the 6th minus 1. And the difference is that this number right here is not a prime. This is 15. And then 2 to the 6th minus 1, that's 63. These are non-primes. So the numbers that worked are the Mersenne primes, right? 1 less than powers of 2. Okay, so let's go ahead and test numbers of this type to see if this always works. So let's let n be a number of the form 2 to the p minus 1 times 2 to the p minus 1. And we'll see as we go along whether we need this to be a prime. Do we need this to be prime? And let's calculate sigma of n. Now, why do I get to say this? Since these two numbers are plainly relatively prime. This is a power of 2, and this is an odd number, so they have no common factor, and sigma is multiplicative. So sigma of n looks like this. All right, sigma of 2 to the p minus 1 is just a geometric sum, which would be 2 to the p minus 1 over 2 minus 1. And sigma of 2 to the p minus 1, well, if this is a prime, let's suppose that it is a prime, then sigma of a prime is just one more than itself. So that would just be 2 to the p if 2 to the p minus 1 is a prime. And if it's not a prime, it's going to be bigger than this number. Okay, so let's go ahead and do the calculation assuming it's a prime. Then what do I get? I get 2 to the p minus 1 times 2 to the p. Okay, that looks awfully familiar. So n is 2 to the p minus 1, so I just pull off one of the 2's, and what I'm left with is n. So 2 times n, which implies that n is perfect. Okay, so whenever 2 to the p minus 1 is a prime, in other words, it's a Mersenne prime, we end up with a perfect number. We've discovered a perfect number. If 2 to the p minus 1 was not a prime, then what would happen is that the sigma here would be strictly bigger than 2 to the p. And so you would have instead a greater than if 2 to the p minus 1 is composite. And so you would end up with an abundant number. You'd have sigma of n is greater than 2n if 2 to the p minus 1 is composite. So that leads us to the question of a converse statement. Does this characterize all of the perfect numbers? Well, there's a theorem that Euler was able to prove. So Euclid was able to prove that one direction we just went through. But Euler turned around and proved a partial converse. It says this: if we start with an even number that's perfect, then n must have the form we just looked at. So an even number is perfect if and only if n is of the form 2 to the p minus 1 times 2 to the p minus 1 for some prime p such that 2 to the p minus 1 is a Mersenne prime, which means is a prime. So we see that there are infinitely many even perfect numbers if and only if there are infinitely many Mersenne primes. So every time you have a Mersenne prime, you get a new even perfect number. So again, Euclid established the sufficiency in this theorem. He did that in his Elements. And then Euler, almost 2,000 years later, established the converse statement. So there remains the open problem of whether there are any odd perfect numbers. So this theorem is just addressing even perfect numbers. What is known is that if n is an odd perfect number, then it must be at least 10 to the 1500 power. That it must have at least 9 distinct prime factors, and that the largest of those factors must be at least 10 to the 8th power, 100 million. So you're not going to try to get lucky just taking a number on a computer and hoping that you found an odd perfect number. It's going to be an enormous number with lots of prime factors. Okay, let's look at the proof. So we want to show that if I'm given an even perfect number, so let n be an even perfect number, and I want to prove that n has that type of form. So let's say n is 2 to the k power times m for some k. Now being an even number means k is at least 1, and odd m. All right, so being perfect means that sigma of n is 2n, which means that sigma of 2 to the k m is 2 to the k plus 1 m. Sigma is multiplicative, so this is sigma of 2 to the k times sigma of m. Which implies that this is 2 to the k plus 1 minus 1 times sigma of m is 2 to the k plus 1 times m. Okay, now what's our goal? I want to show that the m part really looks like that Mersenne prime, that m really is 2 to the k plus 1 minus 1, and that this is a prime. So look at what we've got right here. So m, we want to show, matches up with this object here, and then sigma of m would match up with this guy right here, which would be 1 less, or 1 more than that. Okay, so we're going to suppose the contrary, that m does not equal this, and see what goes wrong. Suppose it doesn't equal this. And let's call this equation star right here. So note, star is telling me that this number, 2 to the k plus 1 minus 1, is a divisor of m. So by star, is a divisor of m. Why is that? Well, it divides this product, and it's clearly relatively prime to 2 to the k plus 1. Since 2 to the k plus 1 minus 1, which is an odd number, is relatively prime to this number. So this is a divisor of m, and I want to create a number of distinct divisors, and it's not going to equal m by this condition right here. So thus, rather than look at this divisor, let's look at its complement, or the divisor pair, which would be m over this. I want to come up with some big divisors of m. So I claim that these are distinct divisors of m. One, m over 2 to the k plus 1 minus 1 and m are distinct. Why are these distinct? Well, we've made the supposition that m doesn't equal 2 to the k plus 1 minus 1. So this does not equal 1, in other words. And then going on right here, how come these two are distinct from one another? That's because k is at least 1. So k being at least 1 means that 2 to the k plus 1 minus 1 doesn't equal 1. Okay, so these are all distinct divisors. So I claim we're going to run into a contradiction if we look at equation star, because what does star say to you? Star is telling us that sigma of m should be almost exactly equal to m. And why is that? It's because 2 to the k plus 1 minus 1 is almost the same size as 2 to the k plus 1. Therefore, this piece here has to match up with that piece. But I claim sigma of m is going to be too big because we have this extra divisor right here. When I look at sigma of n, I have to add up these three numbers. And that's going to be too big for this equation here to hold true. Okay, let's prove that. So I'm going to write down the equation star again. So in the equation star we have 2 to the k plus 1 minus 1 times m, no, times sigma of m, equals 2 to the k plus 1 times m. Right, so that's the equation star. And then we're going to write down these three distinct divisors. So sigma of m is at least the sum of those distinct divisors. There may be further divisors, but it's at least this big. And then let's plug that in to star. So then from star, we would get that 2 to the k plus 1 m, let me switch sides, is greater than or equal to 2 to the k plus 1 minus 1 times this thing right here. And then expand that out. Or just equal. What is it? Equal. So 2 to the k plus 1m is greater than or equal to 2 to the k plus 1 minus 1. And then multiplying this by the second term just gives us an m. And then multiplying it by the third term gives you 2 to the k plus 1 m minus m. The m's cancel. Cancel this on both sides. And I get that 2 to the k plus 1, put the 1 over to the left. 2 to the k plus 1 is less than or equal to 1, a contradiction. So, therefore, we must have, what was I contradicting? This was leading to the contradiction. I must have m equals this. Thus, m equals 2 to the k plus 1 minus 1. And then returning to star up on top, the circled star up above, we get sigma of m equaling 2 to the k plus 1, which equals m plus 1. And the only way sigma of m can be 1 more is if the only divisors of m are 1 in itself, which implies that m is a prime. QED. So m is of the Mersenne type, 2 to the k plus 1 minus 1, and this must in fact be a prime number.